And now in this lecture we'll answer two questions. In the first question, we find out the value of angle AMQ is equals to x. We have to find out the value of angle x. And in the second question, we'll find out the area of this circle that is inscribed by trapezoid ABCD. Repeat again. We'll find out the area of this circle that is inscribed by trapezoid ABCD. So let's start with the first question. In the drawing, we have a semicircle. This is a semicircle. AB is of course the diameter of this semicircle. Point O is the center of this circle. In addition, we know that line segment OS is equal to line segment SB. Inside this semicircle, we have square PQSO. This is square PQSO. Again, our task is to find out the size of angle AMQ that is equal to x. We have to find out the value of x. So first of all, we know that all the angles in any square are right angles. So this is a right angle. This is also a right angle. And this is also a right angle. AB is the diameter of this semicircle. AB is the diameter, it is absolutely a straight line. So if we focus on the upper side of the straight line AB at point S, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line AB at point S? We have this angle that is right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. We know that all the sides of any square are equal to each other. That is to say, side QS is equal to side OS. Here, side QS equals to side OS. QS equals to OS. And it is given us the equation that OS equals to SB. So from this equation, OS equals to QS equals to SB, we will derive that QS equals to SB. QS equals to SB. QS equals to SB. In the next step, we will join points B and Q together by a straight line. And we will extend line segment BQ by a straight line until it touches the circle. And we will define the touching point of the extended line, line segment QB with this circle. This point is point N. In the next step, we'll focus on this right triangle QSB. This is the right triangle QSB. We have the rule that in front of equal sides in a triangle there are equal angles. So in front of those two equal sides in the right triangle QSB, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle as y, then the size of this angle must be also equal to y because they are equal to each other. We also know that the sum of the angles in any triangle is equal to 180 degrees. So the sum of the angles in the right triangle QSB is equal to 180 degrees. So which angles we have in the right triangle QSB? We have y plus y, that is 2y plus 90 degrees. In total, The sum of those two angles must be equal to 180 degrees according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So in the right triangle QSB, we found out that two y plus 90 degrees equals to 180 degrees. Here we subtract 90 degrees from the equation, and we get that 2y equals to 180 degrees plus 90 degrees is 90 degrees. So 2y equals to 90 degrees. Here we divide this equation by 2 and finally get that the missing angle y equals to 90 degrees over 2, that is 45 degrees. So this angle y equals to 45 degrees in its size, and this is also angle y that is equals to 45 degrees in its size. We joined points B and Q together by a straight line, and then we extended the straight line BQ by a straight line. In this way we got line segment BN. When you extend the straight line by a straight line, the result is a straight line. Therefore, BN must be a straight line. Again, BN is a straight line. So if we focus on the left side of the straight line BN at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of the straight line is equal to 180 degrees. So the sum of the angles of the left side of the straight line NB at point Q must be equal to 180 degrees according to rule 3. So which angles we have at the left side of the straight line NB at point Q? We have this angle equals to 45 degrees in its size. Plus this angle, that is a right angle, it is one out of 4 angles of square ABCD, so it is equal to 90 degrees in its size. Plus this missing angle, that is actually angle NQP. In total, the sum of those three angles must be equal to 180 degrees according to rule 3. And again, if we found out that if we focus on the left side of the straight line NB at point Q, the sum of the angles must be equal to 180 degrees according to rule 3. So 45 degrees plus 90 degrees plus the missing angle NQP, in total they must be equal to 180 degrees. Here we subtract 45 degrees plus 90 degrees is 145 degrees. So we subtract 135 degrees from this equation, and we get that the missing angle NQP is equal to 180 degrees minus 135 degrees is 45 degrees. Okay, this is the missing angle NQP that is equal to 45 degrees in its size. In the next step, we'll join points M and N together by a straight line. But again, we'll join points M and N together by a straight line. And we also join points N and A together by a straight line. Again, we join points N and A together by a straight line. By joining points M and A, we created peripherical A and B. This is peripherical A and B. Peripherical A and B subtend on AB, that is the diameter of this semicircle, and therefore according to rule 7, peripherical A and B must be equal to 90 degrees in its size. So repeat quickly rule 7. According to rule 7, if a peripherical subtends on the diameter of the circle, then it is equal to 90 degrees in its size. In the drawing, we have a circle. This is peripherical AQB that subtends on AB, that is the diameter of this circle, and therefore, according to this rule 7, peripherical ACB must be equal to 90 degrees in its size. So we can actually implement rule 7 in our drawing. When because in our drawing, we have peripherical A and B that subtend on AB, that is the diameter of the semicircle, and therefore according to rule 7, peripherical A and B must be equal to 90 degrees in its size. Here we can implement rule 16, because we have, this is peripherical NBA, peripherical NBA is equal to 45 degrees in its size, and it's subtend on chord NA. Again, peripherical NBA that is equal to 45 degrees in its size, subtend on this chord called NA. Likewise, we have also peripherical MNB. This is peripherical MNB that is also subtend. This is actually peripherical peripherical NMA. This is peripherical NMA. Peripherical NMA also subtend on the same chord called AN. But again, those two peripherals, this is peripherical NMA, and this is peripherical NBA. Those two peripherals are both subtend on the same chord called AN, and therefore they are equal to each other according to rule 16. So repeat quickly rule 16. According to rule 16, peripheral angles that subtend on the same chord are equal to each other. In the drawing, we have a circle. This is peripherical AOB that subtend on chord AB. Likewise, we have the other peripherical ACB that is equal to beta degrees in its size, and it also subtend on the same chord called AB. And because of the fact that those two peripherals are both subtend on the same chord called AB, they must be equal to each other in their sizes. That is to say, peripherical AOB must be equal to peripherical ACB, or alpha equals to beta. So we can actually implement rule 16 in our drawing. Because in our drawing, we have peripherical NBA that subtend on chord AN, and we have peripherical NMA that is also subtend on the same chord called AN. And therefore, those two peripherals subtend on the same chord called AN, and therefore peripherical NMA must be equal to 45 degrees in its size. This is actually, this is peripherical NMA. This is peripherical NMA. It is also subtend on the same chord called AN, and therefore it is equal to 45 degrees in its size according to rule 16. So in the next step, we'll focus on this right triangle, triangle A and B. In triangle A and B, this angle equals to 45 degrees inside, this angle equals to 90 degrees, and therefore this third missing angle must be also equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So this missing angle NAB must be also equal to 45 degrees in its size. So in the big right triangle A and B, in front of those two equal angles, we have those two sides that must be also equal to each other and their lengths. That is to say, side AN equals to side NB. Those two sides are equal to each other in the big right triangle, triangle A and B. Therefore, triangle A and B is an isosceles triangle. Because those two sides are equal to each other, and the base of this isosceles triangle, triangle A and B, is AB. So now we should all know that triangle A and B is an isosceles triangle. Because side NA equals to side NB. So triangle A and B is an isosceles triangle. So here we can implement rule 24 in our drawing. Please click on rule 24. According to rule 24, the perpendicular to the base of an isosceles triangle bisect the base. In the drawing, we have the isosceles triangle, triangle ABC. Triangle ABC is an isosceles triangle because side AB equals to side AC. The base of the isosceles triangle, triangle ABC, is BC. According to this rule 24, the perpendicular to the base BC, so the perpendicular from point O to the base BC, that is to say, the perpendicular AO to the base BC bisects base BC. First of all, AO is a perpendicular, and therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. And according to this rule 24, the perpendicular AO to the base BC bisects the base BC. That is to say, it divides the base BC into two halves. The first half is BO and the second half is OC. Each half equals to BC over 2, of course. So the first half is BO, the second half is OC, and each half equals to BC over 2. So BO equals to OC equals to BC over 2. So we can actually implement rule 24 in our drawing. Why? Because in our drawing, we have the isosceles triangle, triangle A and B. Triangle A and B is an isosceles triangle because side AN equals to side NB. AB is the isosceles triangle, triangle A and B. Again, AB is the base of the isosceles triangle, triangle A and B. But AB is also the diameter of the semicircle. But again, AB is simultaneously the diameter of this semicircle, and it is also the base of this isosceles triangle, triangle A and B. So AB is the diameter, so if the radius of this circle is R, then the diameter AB must be equal to 2R. So AB is the diameter of the semicircle is equal to 2R, and AB is also the base of isosceles triangle, triangle A and B. So according to rule 24, the perpendicular from point N to the base AB bisects the base AB. That is to say, it divides the base AB into two halves. Each half must be equal to AB over 2. AB over 2 is 2R over 2, that is R. So the first half is R and the second half is also R. The perpendicular from point N to the base of the isosceles triangle, triangle A and B bisect the base AB. And therefore, the perpendicular from point N must touch side AB at the midpoint of AB. Again, the perpendicular from point N to the base AB must touch the base AB at the midpoint of the base AB. And you know that AB is the diameter, and the midpoint of any diameter is at the center of the circle. Again, the midpoint of any diameter is at the center of the semicircle. The center of the semicircle is at point O. So the perpendicular from point N will touch the base AB at point O, because it bisects the base. Therefore, it must touch the base at the midpoint of AB. The midpoint of AB is the midpoint of the diameter AB, and the midpoint of any diameter is at the center of the circle or the semicircle, and O is the center of the semicircle. Therefore, the perpendicular from point N to the base AB that bisects the base AB must touch AB at point O and not in any other point. So okay, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. The perpendicular NO bisects the base AB. The base AB in total equals to 2R, because it is the diameter of the semicircle also. So each half must be equal to R. The first half AO is R, and the second half OB is also R, and the perpendicular from point N must touch the base AB at its midpoint, and the midpoint of AB is the midpoint of the diameter AB, that is the center of the semicircle, that is at point O. So the perpendicular from point N to the base AB must touch the base AB at point O, that is the midpoint of AB, that is also the center of the semicircle. We know that the opposite sides of a square are parallel to each other. Again, the opposite sides of a square are parallel to each other. So in square PQSO, side PQ is parallel to the opposite side OS. Again, PQ is parallel to OS. Those two angles are defined as corresponding angles, and they are located between the parallel lines PQ and OS. And we have the rule that corresponding angles that are located between parallel lines are equal to each other. In the moment we have line 1 that is parallel to line 2. In addition, we have line 3 that cuts the two parallel lines 1 and 2 at those 2 points. Those two angles, 1 and 2, they are defined as corresponding angles, and they are located between the parallel lines line 1 and line 2. And therefore, they are equal to each other. That is to say, line 1 is equal to line 2. So we can implement this rule in our drawing. In our drawing, we have those two corresponding angles that are located between the parallel lines AQ and OS, and therefore they must be equal to each other on their sizes. But the size of this angle is 90 degrees, and therefore the size of this angle must be also equal to 90 degrees, according to the rule that corresponding angles between parallel lines are equal to each other. So this angle equals to 90 degrees in its side, according to the rule I mentioned. So those two angles are both equal to 45 degrees in their sizes, and the base of those two angles, that is to say angle NMP and angle NQP, the base is NP. And therefore, quadrilateral NMQP, this is quadrilateral NMQP, is a cyclic quadrilateral. Repeat again, quadrilateral NMQP is a cyclic quadrilateral because we have those two angles that are equal to 45 degrees in their sizes, and they subtend on the base NP or chord NP. So I proved why quadrilateral NMQP is a cyclic quadrilateral. A cyclic quadrilateral is a quadrilateral that can be blocked by a circle. So first of all, we know that any triangle can be blocked by a circle. Any triangle is a cyclic triangle. So this is triangle NQP. This angle is angle NQP. So triangle NQP is a cyclic triangle. That is to say, we can block this triangle NQP by a circle. So I block this triangle NQP by a circle, and this is angle NQP that is equals to 45 degrees in its size. So if we take this angle that is equal to angle NQP is equal to 45 degrees in its size. So if we rotate angle NQP in such a way that the axis will be NP, and we rotate angle NQP in such a way that we will not change the size of angle NQP, that is 45 degrees. This way, by rotating angle NQP around this circle, we create infinite angles that each of them will be equal to 45 degrees in size, because we rotate angle NQP in such a way that we will not change the size of the angle. In this way, we create infinite angles that each of them is equal to 45 degrees in its size. One of those two angles, of those two infinite angles, will be angle NMP. This is angle NMP. This is angle NM. This is angle NMP. Again, this is angle NMP. This is also equals to 45 degrees in its size, and it's subset of the same line 7 and line 7 NP. So this is angle NMP, the subset on chord NP. So by rotating angle NQP is equals to 45 degrees in its size around this circle, we create this angle NMP is equals to 45 degrees in its size. In the next step, we join points M and Q together by a side line. So actually, by doing those constructions, we get the quadrilateral NMQP. You can see that quadrilateral NMQP is blocked by this circle. So in this way, actually prove that quadrilateral NMQP is a cyclic quadrilateral. Repeat again. First of all, I blocked triangle Q and P by a circle. This is angle NQP that is equal to 45 degrees in its size. According to the rule that any triangle can be blocked by a circle, triangle NQP can be blocked by this circle. Then we define the NP as the base, and we rotate angle NQP that is equal to 45 degrees in size without changing the size of this angle. We rotate this angle around the circle without changing the size of this angle that is 45 degrees in its size. One of the angles that will be created by rotating angle NQP around this circle will be angle PMN. Angle PMN is also equal to 45 degrees in size, and we join points M and Q together by side line. By doing all those constructions, actually created here quadrilateral MNQP. In this way, actually prove that quadrilateral MNQP is a cyclic quadrilateral. That is to say, it can be blocked by a circle. So quadrilateral NMQP is inscribed by a circle because of the fact that all its four vertices N, M, Q, and P attaches this circle. So quadrilateral NMQP is inscribed by this circle. So in this way, actually prove that quadrilateral NMQP is a cyclic quadrilateral. So we can block quadrilateral NMQP by a circle. So I block this quadrilateral NMQP by a circle. You can see that all the four vertices N, Q, M, and N touches the circle. So this quadrilateral NMQP is inscribed by this red circle. Here we have the rule that states that the sum of the opposite angles in a cyclic quadrilateral is equal to 180 degrees. Again, the sum of the opposite angles in a cyclic quadrilateral is equal to 180 degrees. So, quadrilateral NMQP is a cyclic quadrilateral because it blocks this quadrilateral by this red circle. So, according to this rule that I mentioned, the sum of its two opposite angles, those two opposite angles must be equal to 180 degrees. That is to say, this is angle NPQ, angle NPQ plus this is angle NMQ. In total, the sum of those two angles must be equal to 180 degrees. So let me know, we found out that this is angle NPQ plus the opposite angle, that is angle NMQ, in total the sum of those two opposite angles must be equal to 180 degrees according to the rule that I mentioned. Angle NPQ, this is angle NPQ, that is a right angle, plus this is angle NMQ. Angle NMQ equals to 45 degrees plus x. Again, angle NMQ in total equals to 45 degrees plus x. And it is equals to 180 degrees. 90 degrees plus 45 degrees is 135 degrees. Plus the missing angle x equals to 180 degrees according to the rule that I mentioned, that the opposite angles, the sum of the opposite angles in a cyclic quadrilateral must be equal to 180 degrees. So here we subtract 125 degrees from this equation, and we get that the missing angle x, that is the angle that we are looking for in this question, is equal to 180 degrees minus 125 degrees is 45 degrees. So the answer to the question is that the size of this missing angle AMQ is equals to x. The size of the missing angle AMQ is equals to x is equal to 45 degrees in its size. And again, this is angle AMQ, this is equals to x is equals to 45 degrees in its size. So we finished with the first question. In the next step, I'll present to you the second question of this lecture. In the second question, our task is to find out the area of this circle that is inscribed by this trapezoid ABCD. So in the drawing we have trapezoid ABCD that blocks this circle, or this circle is inscribed by trapezoid ABCD. Those two angles are both right angles. We also know that side AB of trapezoid ABCD equals to 3 units in its length. The area of trapezoid ABCD equals to 3 square units in its size. Again, the area of this trapezoid ABCD equals to 3 square units in its size. Again, our task is to find out the area of this circle that is inscribed by trapezoid ABCD. So first of all, we define relevant points to this question with letters. We define the point of tendency of tangent DC with this circle. This point is point E. We define the center of this circle. This point is point O. We define the point of tendency of tangent CB with this circle. This point is point F. We define the point of tendency of tangent AB with this circle. This point is point G. We define the radius of this circle as x. In the next step, we will join points O and G together by a straight line. Point O is the center of the circle, point G is the point of the circle itself, therefore OG is the radius of this circle, that is equals to x according to our definition. Here we can implement rule 1 and repeat quickly on rule 1, and we will implement rule 1 a couple of times. I will explain only one case, and in the other cases we will implement rule 1 automatically without any explanation. So according to rule 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So in the moment we have a circle, tangent AB is tangent to this circle, and this point M. The radius OM, that is equals to R, the radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. Again, if AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to this rule 1. So we can actually implement rule 1 in our drawing. Because in our drawing, we have the radius OG, this equals to x, the radius OG is drawn to point G, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius GO. If AB is perpendicular to GO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. We join points O and E together by a straight line. OE is of course the radius of this circle, that is equals to x. Here according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. We define the point of tendency of tangent DA with this circle. This point is point H, and we join points O and H together by a straight line. OH is of course the radius of this circle, is equals to x, and according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in the upper quadrangle DEOH, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth angle, in total it must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees, and therefore this fourth angle must be equal to 90 degrees in its size. So in quadrangle DEOH, we have 4 right angles. And therefore, according to rule 5, quadrangle DEOH must be at least a rectangle if not a square. So we need to quadrangle DEOH as a rectangle because it has 4 rectangles. So rectangle DEOH, side EO must be equal to the opposite side DH. But EO equals to x, therefore the opposite side DH must be also equal to x units in its length. Likewise, in the lower quadrangle AOGA, we have 1, 2, 3 rectangles, and therefore this fourth missing element must be equal to 90 in size. I will not repeat on the same explanation. For the lateral edge of GA, there is 4 rectangles, and therefore can relate for the lateral edge of GA is a rectangle, but we know that the opposite sides of a rectangle are equal to each other. So rectangle edge of GA, side OG must be equal to the opposite side AJ. But OG is x, therefore the opposite side AJ must be also equal to x units in its length. So in total, we found out that dA in total equals to x plus x, that is 2x. Again, dA equals to x plus x, that is 2x. dA is definitely a straight line because dA is one side of trapezoid ABCD, that is also absolutely a straight line. So dA in total equals to 2x units in its length. In the next step, we define the length of side DC as A. That is to say, side DC equals to A units in its length according to our definition. Actually, in the previous lecture, we proved that DA plus CB equals to DC plus AB. We have already proved that dA plus CB equals to DC plus AB. We proved this statement according to rule 2. So I'll not repeat on the proof, and we will use the proof in this lecture. So we already proved that dA plus CB equals to DC plus AB. So write it down. dA plus CB equals to DC plus AB. Repeat again. In trapezoid, ABCD, we want to prove that dA plus CB equals to DC plus AB. dA is A plus CB. CB is the missing side, so we leave this it is. And it is equals to this is side dA, is equals to 2x. Again, this is side dA. This is side dA, that equals to 2x. Again, dA equals to 2x and not 2a. dA equals to 2x plus CB. CB is the missing side, so remove it is. And it is equals to DC. DC equals to A. Okay, DC equals to A plus AB. AB equals to 3 units in its length according to what is given in the question. So in total, we should find out that dA plus CB equals to 2x plus CB. On the other side of the equation, we have DC plus AB, that is A plus 3. So in total, if we found out that 2x plus CB equals to A plus 3. Here we subtract 2x from this equation. And we get that CB, the missing side CB of trapezoid ABCD, is equal to A plus 3 minus 2x. And again, if you found out that the missing side CB of trapezoid ABCD equals to A plus 3 minus 2x. This is the missing side CB. This is equals to a plus 3 minus 2x. A plus 3 minus 2x. In the next step, we will do a construction. That is to say, from point C, we will draw perpendicular on AB. Again, from point C, we will draw perpendicular on AB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB. This point is point M. By doing this construction, we can deduce the big quadrilateral DCMA. This is the big quadrilateral DCMA. In the big quadrilateral DCMA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the side of this 4 angle. In total, the mass will equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this 4 angle must be equal to 90 degrees in its sides. So inside quadrilateral DCMA, we have 4 right angles, and therefore can relate to quadrilateral DCMA as a rectangle. So if you found out that the big quadrilateral DCMA is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle DCMA, side DC must be equal to the opposite side CM. But DC is 2x, therefore the opposite side CM must be also equal to 2x units in its length. Likewise, according to the same rule, in the same rectangle DCMA, side DC must be equal to the opposite side AM. But DC is A, therefore the opposite side AM must be also equal to A units in its length. So A equals to A units in its length. So what is the value of the, what is the length of the missing side? 97 GM. What is the value of this missing 97 MB? From the drawing, it is very easy to see that MB in total equals to AB minus AM. And MB equals to AB minus AM. So that's it down. The missing 97 MB is equal to AB minus AM. So MB in total equals to AB is 3 according to what is given as the question, minus AM. We just now found out that AM equals to A. So in total MB equals to 3 minus A units in its length. MB equals to 3 minus A units in its length. Again, MB equals to 3 minus A units in its length. In the next step, I will copy the right triangle CMB in a new page and implement the Pythagoras theorem in this right triangle CMB. Side CM equals to 2x, side MB equals to 3 minus A units in its length, and the hypotenuse CB equals to A plus 3 minus 2x units in its length. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So I copy this right triangle CMB and we implement on this right triangle CMB the Pythagoras theorem. Here by PT is the evaluation for Pythagoras theorem. So actually, this is the right triangle CMB that according to the original domain. This right triangle CMB, according to the Pythagoras theorem, CB squared, that is the square of the hypotenuse, equals to CM squared plus MB squared. So I write it down. CB squared, that is the square of the hypotenuse, equals to CM squared plus MB squared. CB, the hypotenuse CB equals to A plus 3 minus 2x. Therefore, CB squared equals to A plus 3 minus 2x squared. And it is equals to CM squared. CM is 2x, therefore CM squared is 2x squared, that is 4x squared, plus MB squared. MB is 3 minus 8, therefore MB squared is 3 minus 8 squared. So in total, according to the Pythagoras theorem, if we found out that A plus 3 minus 2x squared equals to 4x squared plus 3 minus 8 squared. Here we will open the brackets on both sides of this equation. We'll open the brackets of this expression according to the algebraic identity that says that A minus B squared equals to A squared plus B squared minus 2 times A times B. A is A plus 3 and B is 2x. So, according to the algebraic identity that I mentioned, A plus 3 minus 2x squared will be equal to A plus 3 squared plus 2x squared, that is 4x squared, minus 2 times A plus 3 times 2x. And it is equals to 4x squared and plus 3 and minus a squared. 3 minus a squared equals to 3 squared, that is 9, plus a squared, minus 2 times 3 times a, that is minus 6a. We'll open the brackets of this expression. A plus 3 squared equals to a squared plus 3 squared, that is 9, plus 2 times a times 3, that is plus 6a, plus 4x squared, minus 2 times 2x is minus 4x. So the brackets we have a plus 3 equals to 4x squared plus 9 here we have 9 plus a squared. 3 minus a squared is 9 plus a squared. Minus 6a. Here we have a squared on both sides of this equation, so a squared will get cancelled. We have 9 on both sides of this equation, so 9 also will get cancelled. We have 4x squared on both sides of this equation, so 4x squared also will get cancelled. After we cancel those expressions, we left in this side of the equation only with 6a minus 4x a plus 3 equals to another side of the equation we left only with minus 6a. Here we will add 6a to this equation and also minus, we will add also 4x times a plus 3 simultaneously to this equation. We get that 6a plus 6a is 12a equals to 4x times a plus 3. Here we divide this equation by 4 and we get that 12 over 4 is 3, so here we have 3a equals to 4x over 4 is x times a plus 3. So in total we found out that 3a equals to x times a plus 3. Here we divide this equation by a plus 3. And finally we get that x equals to a plus 3, x equals to 3a over a plus 3. And again, if we found out that in total x equals to 3a over a plus 3. X equals to 3a over a plus 3. We know that the area of this trapezoid ABCD is equals to 3 square units. Repeat quickly on the definition of a trapezoid. A trapezoid is a quadrilateral with one pair of parallel sides. Repeat again. A trapezoid is a quadrilateral with one pair of parallel sides. This is quadrilateral ABCD. In quadrilateral ABCD, side DC is parallel to the opposite side AB, and therefore quadrilateral ABCD is defined as a trapezoid. So in trapezoid, because it has one pair of parallel sides. So in trapezoid ABCD, the base DC is parallel to AB, so the two parallel sides are defined as the bases of this trapezoid ABCD. So if we define the base DC as A and the base AB as B, that is to say AB equals to B unity in itself according to our definition, then the area of this trapezoid ABCD must be equal to the sum of its two parallel bases, that is to say A plus B, times the height edge over 2. The height edge must create 90 degrees with the two parallel bases. You can see it is create 90 degrees with the two parallel bases. So a trapezoid is a quadrilateral with one pair of parallel sides, and the area of a trapezoid is equal to the sum of its two parallel bases. In this case, it is A plus B times the height edge over 2. And the height edge must create 90 degrees with the two parallel bases. So according to the formula that I presented to you, the area of this trapezoid ABCD must be equal to the sum of its two parallel bases. The two parallel bases are DC and AB, so it is DC plus AB times the height. The height is CM. Why CM is the height? Because it has 90 degrees with the two parallel bases. So times the height CM over 2. And again, if we found out that the area of this trapezoid ABCD in total is equal to the sum of its two parallel bases, DC plus AB, times the height CM over 2. DC is A plus AB. AB is 3. According to what's given us in the question, AB equals to 3 units in itself. times cm. cm is 2x divided by 2. So in total, if you know that the area of this trapezoid ABCD equals to a plus 3 times 2x over 2. We have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. So we left only with a plus 3 times x. And it is equals to the area of trapezoid ABCD. So the area of trapezoid ABCD equals to a plus 3 times x square units in its size. But it is given as the question that the area of this trapezoid ABCD equals to 3 square units in its size. So we can substitute the area of trapezoid ABCD by 3 and get that 3 equals to a plus 3 times x. Again, 3 equals to a plus 3 times x. But we already found out that x equals to 3a over a plus 3, so we can substitute x in this equation by 3a over a plus 3. And do it now and get that 3 equals to a plus 3 times x, and x equals to 3a over a plus 3. We have a plus 3 in the numerator and a plus 3 in the denominator, so a plus 3 will get cancelled. Like I said, a plus 3, we left only with 3 equals to 3a. Here we divide this equation by 3 and finally get that a equals to 1. A equals to 1. So if we found out that a equals to 1 unit in its length, and x equals to 3a over a plus 3. Now we'll substitute a in this equation by 1 and we get that x equals to 3 times 1, 3a is 3 times 1, that is 3, over a plus 3. A plus 3 is 1 plus 3, that is 4. So in total we found out that x, that is the radius of this circle that is described by this trapezoid ABCD, the radius of x equals to 3/4 units in its length. Our task is to find out the area of this circle. So actually, we know that the area of any circle is equal to pi times the radius of the circle squared. I repeat again, the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is x squared. So the area of our circle must be equal to pi x squared. So it is pi times x squared. X is 3/4, and therefore x squared is 3/4 squared. So it is pi times 3 squared is 9 over 4 squared is 16. So if you found out that the area that we are looking for in this question, that is the area of this circle, equals to either 16, either equals to 9 pi over 16 square units in its size, or in terms of numbers, the area of this circle equals to 1.767 square units in its size. And again, if you found out that the area that we are looking for in this question, that is the area of this circle, is equals to either 9 pi over 16 square units in size, or in terms of numbers, the area of this circle equals to 1.767 square units in size. So we finish with the second question. In the next step, I'm starting with the lecture. We'll start with the first question, of course. In the first question, our task was to find out the size of this angle, angle MAQ, this is equals to x. This is angle MAQ, this is equals to x. We have to find out the value of x. So, in the drawing, we have a semicircle. AB is of course the diameter of this semicircle. Point O is the center of this semicircle. You know that line segment OS equals to line segment SB. Inside this semicircle, we have this square PQSO. Again, our task is to find out the size of this angle MAQ, that is equals to x. We have to find out the value of angle x. So, first of all, we know that all the angles inside the square are right angles. So, those angles are right angles. The square AQSO. AB is the diameter of the semicircle, it is absolutely a straight line. So if you focus on the upper side of the straight line AB at point S, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line AB at point S? We have this angle that is a right angle, plus this missing angle, in total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. We know that in any square, all the sides of any square are equal to each other. So in square PQSO, side QS equals to side SO. QS equals to SO. But it is given in the question that SB equals to OS, SB equals to OS. And from this equation, QS equals to OS equals to SB, we derive that QS equals to SB. QS equals to SB. So those two sides are equal to each other. We focus on the small right triangle QSB. In the small right triangle QSB, in front of this small right triangle QSB, in front of those two equal sides, we have those two angles that must be also equal to each other, according to the rule that in front of equal sides in the triangle there are equal angles. So those two angles are located in front of those two equal sides, and therefore they must be equal to each other in their sizes. So if we define the size of this angle as y, then the size of this angle must be also equal to y because they are equal to each other. We know that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have in the right small triangle QSB? We have y plus y, that is 2y plus 90 degrees. In total, they must be equal to 180 degrees. According to all that the sum of the angles in any triangle is equal to 180 degrees. So in the right small triangle QSB, 2y plus 90 degrees must be equal to 180 degrees. Here we subtract 90 degrees from the equation, and finally found out that 2y equals to 180 degrees minus 90 degrees is 90 degrees. So 2y equals to 90 degrees. Here we divided this equation by 2 and found out that angle y equals to 90 degrees over 2, that is 45 degrees. So those two angles, each of them is equal to 45 degrees in its size. In the next step, actually, before that, we have already joined points B and Q. In this way, we created the right triangle QSB. After we joined points B and Q by straight line, we extended the straight line BQ until it touches the circle at this point. We define the touching point of the extended segment BQ with this circle. This point is point N. When we extend the straight line by straight line, the result is a straight line. So BN is a straight line. So if you focus on the left side of the straight line BN at point Q, with the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of the straight line BN at point Q? We have 45 degrees plus 90 degrees plus this missing angle NQP. In total, must be equal to 180 degrees according to rule 3. Repeat again. If we focus on the left side of the straight line AB at point Q, the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the left side of the straight line AB at point Q? We have 45 degrees plus 90 degrees plus the missing angle NQP, total must be equal to 180 degrees. Here we subtract 45 degrees plus 90 degrees is 135 degrees. So we subtracted 135 degrees from the equation and finally found out that the missing angle QP equals to 180 degrees minus 135 degrees is 45 degrees. Actually, this is the missing angle NQP. This is equals to 45 degrees in its size. In the next step, we join points M and N together by side line. And we join points N and A together by side line. By doing this construction, we can do the peripheral angle NAB. This is peripheral angle NAB. Peripheral angle NAB. This is peripheral angle NAB. The subtend on AB. That is the diameter of this semicircle. And we know that any peripheral angle that subtend on the diameter of the circle or semicircle must be equal to 90 degrees in its size. Therefore, peripheral angle AB equals to 90 degrees in its size. So the big right triangle NB, this angle equals to 45 degrees. This angle equals to 90 degrees, and therefore this angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So in the right big triangle A and B, in front of those two equal angles, we have those two sides that are also equal to each other, according to the rule that in front of equal angles in the triangle, they are equal sides. So side NA equals to side NB, and therefore the big right triangle A and B is an associated triangle. Because of the fact that the big triangle A and B is an associated triangle, we have the rule 24 that says that the perpendicular to the base of an associated triangle bisects the base. The base of the right triangle A and B is AB. So the perpendicular from point N to the base AB bisects base AB. AB is also the diameter of the semicircle. AB is the diameter of the semicircle. If the radius of this semicircle is R, the diameter must be equal to 2R. So AB equals to 2R. And if the perpendicular from point N to the base AB bisects the base AB, it means that it divides it into two halves. Each half must be equal to AB over 2. The first half is AB over 2, and the second half is OB over 2. But AB over 2 is 2R over 2, that is R. So the first half, AO is R, that is the radius of the semicircle, and the second half, OB is also R, that is the radius of this semicircle. The perpendicular from point N bisects the base AB. If it bisects the base AB, it means that it touches the base AB at its midpoint. Again, if it bisects for AB, it means that it touches the base AB at its midpoints. And the midpoint of AB, that is the midpoint of the diameter AB, it must be at the center of the semicircle. Because the midpoint of any diameter is the center of the circle of the semicircle. And the center of this semicircle is at point O. Therefore, the midpoint of AB is at point O. That is the center of this semicircle. So the diameter for point N will touch the base AB at point O. That is the center of this semicircle. So AO equals to R, that is the first half, and OB also equals to R, that is the second half of the base AB. And this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction, because from point N we do perpendicular to the base AB. So here we know that the sides of any square are parallel to each other. So in square PQSO, side PQ is parallel to the opposite side OS. So those two angles are defined as corresponding angles, and are located between the parallels PQ and OS, and therefore they must be equal to each other and their sizes. But this angle equals to 90 degrees according to our construction, therefore this angle must be also equal to 90 degrees, because they are equal to each other according to the rule that I mentioned. So here we have those two angles are both equal to 45 degrees in their sizes, and they subtend on the base PN. Therefore, actually, this is quadrilateral QM NQ NMQP. That is a cyclic quadrilateral. That is to say, quadrilateral NMQP can be blocked by a circle. Actually, put why this quadrilateral NMQP can be blocked by a circle. First of all, we know that any triangle can be blocked by a circle. Again, any triangle can be blocked by a circle. So I copy this triangle NQP. This is triangle NQP. There's a copy. This is triangle NQP. There's a copy triangle, and this is angle NQP. This is equals to 45 degrees in its size, and this is triangle NPQ. So this is triangle NQP, that it could be blocked by circle like any triangle. So I block this triangle NQP by a circle. This is the circle that blocks triangle NQP. Then this is angle NQP, that equals to 45 degrees in its size. NP is the axis. I actually rotated angle NQP, that is equals to 45 degrees in size, without changing the size. I rotated angle NQP around the circle without changing the size of angle NQP. When doing this operation, we will create infinite angles that each of them is equal to 45 degrees in its size. One of those angles must be angle PNM, and NMP. This is also equal to 45 degrees in its size. So this is angle NMP, that will be one out of infinite angles that will be created by rotating angle PQN around the circle when NP is the axis and MP doesn't move. So this angle will be created by rotating angle PMN, will be created by rotating angle PQN around this circle without changing the size of this angle, that is 45 degrees. So in this way, created angle PNM, that goes to 45 degrees in its size. In the next step, we join points M and Q together by straight line. Again, we have angle NPQ, that is coming from the original domain, and this is angle NMP, that was created by rotating angle NQP around this circle without changing the size. So in this way, we created it, and we join points M and Q together by straight line. In this way, we created it for the other NMQP. So we actually prove that quadrilateral NMQP is a cyclic quadrilateral. You can see that quadrilateral NMQP is blocked by circle according to my construction. So in this way, I prove that quadrilateral NMQP is a cyclic quadrilateral. It is a cyclic quadrilateral. That is to say, all of its 4 vertices lie on this circle. Okay, so in this way, I prove that quadrilateral NMPQ is a cyclic quadrilateral. That is to say, this is the red circle that blocks quadrilateral NMQP. It blocks quadrilateral NMQP because all of its 4 vertices NMQMP lie on the red circle. So quadrilateral NMQP is blocked by this red circle. Now we can implement the rule that says that the sum of the opposite angles, the sum of the 2 opposite angles in the cyclic quadrilateral is equal to 180 degrees. Again, the sum of the 2 opposite angles in the cyclic quadrilateral is equal to 180 degrees. That is to say, according to the rule that I read, the sum of those 2 opposite angles must be equal to 180 degrees. This is angle NPQ plus this opposite angle, that is angle NMQ. Total, the sum of those 2 angles must be equal to 180 degrees. And again, angle NPQ plus the opposite angle NMQ in quadrilateral NMQP equals to 180 degrees according to the rule that I mentioned. Angle NPQ is a right angle. Angle NMQ equals to 45 degrees plus x in total. And again, angle NPQ is a right angle, and angle NMQ equals to 45 degrees plus x in total. So 90 degrees plus 45 degrees plus x equals to 180 degrees, according to the rule that I mentioned. 90 degrees plus 45 degrees is 135 degrees plus x equals to 180 degrees. So 135 degrees plus x equals to 180 degrees. Here we subtract 135 degrees from this equation, and finally found out that the missing angle x equals to 180 degrees plus 135 degrees is equal to 45 degrees in size. So this is the missing angle AM cubed is equals to x. The missing angle AMA cubed is equals to x is equals to 45 degrees in size. So we finished with the first question. The next time I actually presented you the second question and solve the second question of this lecture. In the second question, our task is to find out the area of this circle that is inscribed by trapezoid ABCD. And again, we have to find out the area of this circle that is inscribed by this trapezoid ABCD. So, in the drawing, we have trapezoid ABCD that blocks this circle. In addition, we know that those two angles are both right angles. And we also know that the area of this trapezoid ABCD equals to 4 square units in size, and side AB equals to 3 units. Again, our task is to find out the area of this circle that is described by this trapezoid ABCD. So first of all, we define the relevant points of this question with letters. We define the point of tendency of tangent DC with this circle. This point is point E. We define the point of tendency of tangent DC with this circle. This point is point E. We define the point of tendency of tangent DA with this circle. This point is point H. We define the point of tendency of tangent AB with this circle. This point is point G. In the next step, we define the radius of this circle as x and the center of this circle as O. We join points O and G together by side line. Point O is the center of the circle, point G is the point of the circle itself, therefore OG is the radius of the circle that is equal to x. The radius OG is equal to x, the radius OG is equal to point G, that is the point of tendency of tangent AB with this circle. Whenever your radius is drawn to the point of tendency, then tangent AB will be perpendicular to the radius GO. If AB is perpendicular to GO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and H together by side line. OH is the radius of the circle that is x, and according to 1, those two angles are both right angles. Likewise, we join points O and D together by side line. O is the radius of the circle that is equal to x, and those two angles are both equal to 90 degrees according to rule 1. So in quadrilateral DEAO, we have 1, 2, 3 degrees. The sum of 3 degrees is 270 degrees, so 270 degrees plus the side of this fourth angle. In total, the must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth angle must be equal to 90 degrees in its size. So inside quadrilateral DEAO, we have 4 angles, and therefore we can relate to quadrilateral DEOH as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So rectangle OHDE side OE must be equal to the opposite side HD. But OE is x, therefore the opposite side HD must be also equal to x units in its length. Likewise, in the lower quadrilateral HOGA, we have 1, 2, 3 rectangles. Therefore, this fourth angle must be equal to 90 degrees inside. Therefore, quadrilateral HOGA, we can relate to it as a rectangle, or those that, in fact, we'll find out that quadrilateral HOGA is a square. We can relate to it as a rectangle. We know that the opposite sides of a rectangle are equal to each other. So the lower rectangle HAGO side OG must be equal to the opposite side AJ. but OG is x, therefore the opposite side AJ must be equal to x units in its length. So in total, dA equals to x plus x, this is 2x. dA is definitely a side line because dA is one side of trapezoid ABCD. So dA equals to 2x units in its length. This is side DC. We define the length of side DC as A. We have in the previous lecture, I want to prove that in any trapezoid, dA plus CB equals to DC plus AB according to rule 2. Again, according to rule 2, dA plus CB equals to DC plus AB. So we will not repeat on the same proof. So use the proof in order to determine that dA plus CB equals to DC plus AB. So in trapezoid ABCD, dA plus CB equals to DC plus AB. dA is 2x plus CB is the missing side, so it is, and it is equals to DC. DC is A plus AB. AB is 3 according to what is given in the question. So in total, we should found out that 2x plus the missing side CB equals to A plus 3. Here we found that 2x from this equation, and we found out that the missing side CB equals to A plus 3 minus 2x units in its length. This is the missing side AB is equal to A plus 3 minus 2x units in its length. In the next step, we did the construction, that is to say, from point C, we do perpendicular on AB. Again, from point C, we do perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB. This point is point M. By doing this construction, we get the quadrilateral DCMA. Inside quadrilateral DCMA, we have 1, 2, 3 degrees. The sum of 3 degrees is 270 degrees, so 270 degrees plus the size of this 4 pieces again, in total it must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4 pieces again must be equal to 90 degrees in its size. So inside quadrilateral DCMA we have 4 degrees, and therefore we can relate to quadrilateral DCMA is 5 degrees because it has 4 degrees. But we also know that the opposite sides of rectangle are equal to each other. So rectangle CMA side DC equals to the opposite side CM, but DC is 2x, therefore the opposite side CM must be equal to 2x units in its length. Likewise, according to the sum rule, the sum of the DCMA side DC must be equal to the opposite side AM, but DC is A, therefore the opposite side AM must be also equal to A units in its length. What is the length of this missing line side MB? MB equals to AB, this is 3, also AM, this is A. So in total, again, MB equals to AB minus AM. So MB equals to AB, that is 3, minus AM, that is A. So in total, MB equals to 3 minus AM in its length. So in the next step, we call it the right triangle CMB. In the new page, we implemented the Pythagoras theorem, but this right triangle CMB. So this is the right triangle CMB, this is a comment from the original drawing. In this right triangle CMB, according to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendicular. So in the right triangle CMB, according to the Pythagoras theorem, CB squared, that is the square of the hypotenuse, equals to CM squared plus MB squared. CB is A plus 3 minus 2x, therefore CB squared is A plus 3 minus 2x squared, and it is equals to CM squared. CM is 2x, therefore CM squared is 2x squared, that is 4x squared, plus MB squared. MB is 3 minus A, therefore MB squared is 3 minus A squared. So total we found out that A plus 3 minus 2x squared equals to 4x squared plus A minus 3 squared. We open the brackets on both sides of this equation. We open the brackets of this side of the equation according to the rule, to the algebraic identity that states that A minus B squared equals to A squared plus B squared minus 2 times A times B. So according to the algebraic identity that I mentioned, A plus 3 minus 2A squared must be equal to A plus B squared plus 2x squared, that is 4x squared, minus 2 times A plus 3 times 2x. And is equals to 4x squared plus 3 minus A squared. 3 minus A squared equals to 3 squared, that is 9, plus A squared, minus 2 times 3 times A, that is minus 6A. we open the bracket of this expression. A plus 3 squared equals to a squared plus 3 squared, that is 9, plus 2 times a times 3, that is 6a, plus 4x squared, plus we have minus 2x is minus 4x, so in total this expression equals to minus 4x times a plus 3, and it is equals to 4x squared plus 9 plus a squared minus 6a. Here we have a squared on both sides of the equation, so a squared gets cancelled. We have 9 on both sides of the equation, so 9 also gets cancelled. We have 4x squared on both sides of the equation, so 4x squared will get cancelled. So after we cancel all those two expressions, we left this out of the equation only with 6a plus 4x times a plus 3, and it is equals to minus 6a. The other side of the equation, we left only with minus 6a. So in total, we found out that 6a minus 4x times a plus 3 equals to minus 6a. We added 6a and also 4x times a plus 3 simultaneously to this equation, and finally found out that 6a plus 6a is 12a equals to 4x times a plus 3. Here we divided this equation by 4, and finally found out that 12a over 4 is 3a equals to 4x over 4 is x. So in total, this expression equals to x times a plus 3. Here we divided this equation by a plus 3, and finally found out actually that x equals to 3a over a plus 3. The area of trapezoid ABCD, according to the formula that I presented to you in the beginning of the lecture, the area of any trapezoid equals to the sum of its two parallel bases. In this case, it is DC plus AB, DC plus AB times the height CM over 2. Times the height CM over 2. DC is A plus AM is 3, and this is A plus AB. AB is 3, according to what is going to the question, times CM. CM is 2x, the height CM is 2x, divided by 2. We have 2 in the numerator and 2 in the denominator, so 2 will get cancelled, and we have only a plus 3 times x. So total, we should know that the area of trapezoid ABCD equals to a plus 3 times x square units in its size. But it is given as the question that the area of trapezoid ABCD equals to 3 square units. So we can substitute the area of trapezoid ABCD by 3. We did it, and we found out that 3 equals to a plus 3 times x. We can substitute x by 3a over a plus 3, because x equals to 3a over a plus 3. We did it, and we found out that 3 equals to a plus 3 times x. So 3 equals to a plus 3 times x. X is 3a over a plus 3. We have a plus 3 in the numerator and a plus 3 in the denominator, so a plus 3 gets cancelled, and we left only 3 equals to 3a. Here we divided the equation by 3, and we found out that a equals to 1. So a equals to 1 units in its length. And we have the equation that x equals to 3a over a plus 3. So we can substitute a by 1, because a equals to 1. We did it, and we found out that x equals to 3a, that is 3 times 1, that is 3. Over a plus 3, a is 1, so a plus 3 is 1 plus 3, that is 4. So in total, we found out that the radius of this circle, x equals to 3 quarters. Our task is to find out the area of this circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is x squared. So in total, the area of our circle must be equal to pi x squared. X is 3 quarters, therefore x squared is 3 quarters squared. 3 quarters squared is 3 squared, that is 9, over 4 squared, that is 16. So in total, we found out that the area that we are looking for in this question, that is the area of this circle, is equal to either 9 pi over 16 square units in size. So in terms of numbers, the area of this circle equals to 1.767 square units in size. Okay, thank you very much.